Thank you very much. So this work is reporting on essentially the PhD thesis of Samantha Benincasa, who just submitted on Monday and is going to very shortly be here in California working with Andrew Wetzel's group at Davis. And a mix of other collaborators who've passed through McMaster at one time or other. And the associated paper has just gone up on arXiv, and we certainly welcome comments. We kind of stuck it there partly to try and get comments, so we're anticipating we'll tweak it as necessary based on your feedback. And so following on from that, what we were motivated by was what the scales of star formation are. We wanted to investigate this, and we know that at the current time, the characteristic sizes of, say, molecular clouds in the Milky Way are relatively small. So it's been argued that the dominant size scale is around 1 million solar masses, and from that you get star clusters on scales between 1,000 and 100,000 solar masses. But when you go to high redshift, you start to get different answers, and we wanted to investigate this. And so, for example, if you look within the candle survey, you can see that the galaxies are very clumpy, and the beams are of order 500 to 500 parsecs to a kiloparsec, and you identify within these images very large clumps, which can take up maybe 10% of the baryonic mass of these galaxies. And there are complementary studies looking at, say, CO, where again you find extremely large clumps with scales of, say, up to 2 to 4 kiloparsecs. Now, there was a remark that the velocity dispersion in these clumps isn't so large as you might expect if they were bound objects. So there's some potential interpretation required to understand what the intrinsic structures inside these are, given that the beams that people are using to observe these things are relatively large on the scale of order kiloparsecs. But one interpretation would be that star-forming structures are considerably larger at high redshift. So again, you might want to study this, and so you can do so using simulations. And Avishai's group, Daniel Severino and company, NEAR, have looked at this using simulations to try and understand the origins of large clumps potentially. So these simulations have been able to generate very large clumps, and of order 1% or larger of the disk mass. And there are also indications that if you apply linear theory, then the tumor AQ is an indicator of where clumps might form within these disks. However, there have also been other groups who've approached this with simulations using slightly different methods, and they've been arguing that, in fact, the clumps are smaller. Caviarello, for example, et al. Have essentially put a ceiling on the clump masses of order 10 to the 8 solar masses. So there's a bit of a discrepancy here within the simulations. So Berendt and Andy Burkett and Schartmann have also looked at this using, again, a different code, and they tried to explicitly investigate this idea of beam smearing by doing very high resolution AMR simulations and then applying the beam smearing to join the clumps together. And so there's definitely kind of a bit of confusion or disagreement perhaps about what you can get from simulations. And a very interesting twist on this happened fairly recently. Rigby et al., Johnson et al., and Livermore et al. Have been looking at lensed galaxies. So here is their observation, which has been deliberately degraded with a wider beam, and you get a very clumpy image. I think the galaxy is around redshift 2. But with the lensing, you can see the galaxy at much higher effective resolution. Now, interpreting this is a little difficult because the lensing is stretching the image in different amounts in different directions. So you need to be fairly clever with how you build the models of this. But as a result of this, they infer relatively small clumps on the scales of, say, 100 parsecs or smaller. And if you interpret this as masses, they're more in keeping with the Milky Way scale stellar clusters. Now, one argument you can make is that this is not necessarily a typical object from candles, right? Because this is a lensed object, you're maybe picking out a more boring galaxy, if you like, maybe closer to a Milky Way analog, less like a candles type object. So again, it's hard to interpret given that you don't have good statistics with the lensing. And there was another fun paper just came out. This is the cosmic snake. You can see it. It's very fun image. So there's two lensed images that they've been looking at within this cluster of galaxies of the same high redshift galaxy. The top left one, which has an effective resolution of 300 parsecs versus the bottom right one, which has an effective resolution of 30 parsecs. And so they can do their analysis on both images, and they come up with a different result for what the clump masses are, which we would just attribute to beam smearing type effects. There's also been some other work that I'd like to point out just briefly, looking at statistics and how clump clustering might contribute this. D. Fisher's work on this, for example, and what the relative role of in situ versus ex situ clumps might be. So you have two interpretations. Their clumps are large or they're small. And so given this dichotomy, one of the things that struck us about this work is that these were different codes, but not just different codes, but different assumptions about the physics that was operating. So different people had simplified equations of state, cooling, etc. People had different feedback recipes in particular, and there's no real agreement on what the ideal feedback recipes are, particularly when you go to high redshift, where I think it's a real free-for-all as to how you're regulating star formation in these objects. So that creates a degree of uncertainty. So we've got a lot of questions to look at, like how are the clumps forming, what are the expected masses, but also is there different physics at high redshift in terms of how star formation is driven, and also this impact of these recipes, how do you disentangle that? And so to try and address this, we tried to look at a simpler question. So we're just only going to look at in situ clump formation in isolated disks. We wanted to essentially try and skip the issue of whether the star formation is different by focusing just on the initial bound clump, and then you can go from there and apply whatever star formation assumptions you want, but we just want to start there. And to avoid the complications of what exact feedback recipe you're using, we just didn't use one. So we just essentially did a very simple simulation, only focusing on the original instabilities that are forming the clumps. So we did this using the gasoline code. This is a sort of modern version of it, which does quite well in capturing instabilities and such. We also used a very high resolution. We have a gas mass of about 1,000 solar masses, so we have no issues with resolving Jeans masses, etc., etc. Now, obviously, given that we're using an isothermal equation of state, things run away and the density gets arbitrarily high, but we can resolve the Jeans mass up to densities of 1,000 atoms per cc or so when these clumps are very much bound, and so we don't concern ourselves with what they do next. The other remark I'd make is that, just as in the previous talks by Hannah and so on, is these disks are very, very turbulent, which is very difficult to capture well in simulations. For example, the people who do turbulent simulations have crazy resolution would still argue that they're not doing a great job. If you look at the people from NCSA, etc., doing boxes with turbulence, they have very, very high resolution and still arguing it's difficult. So we've gone to this isothermal as an alternative. So it provides the necessary support without the uncertainty of whether you're doing a good model of that physics. So that's how we chose that. So we characterize our models in terms of 3 velocity dispersions, 5, 14, and 40 kilometers per second, but that's a proxy for us for a velocity dispersion, essentially. We're using the isothermal equation of state to handle that. We picked a Q-min of about 1.1 at 5 kiloparsecs, so these are theoretically stable to axisymmetric linear modes. And the first thing we did was just put a turbulent velocity spectrum on top with a velocity dispersion slightly higher than the isothermal one, and just sort of see what it does. And so when we do that, the cold disk does what you might expect. It fragments into quite small structures, and we get clump masses that sort of are in the ballpark of what you might expect from Milky Way. The warm one, a little bit larger, but even the very hot one, which might be an analog of a Candles object, we're not really getting up to 10 to the 9 solar masses very easily. But part of the issue with this is that we're not really looking at, we can't really sort of break this down and ask, how does this compare to expectations from linear theory, right? So we wanted to go even simpler and do that. So linear theory often invoked is that sort of just basic tumor theory. You can read Jabini and Tremaine and see endless amounts on this. And so you have a nice dispersion relation, and that reflects the fact that you have no explicit time dependence in your equations, so that you can understand the instability in terms of the dispersion relation. If omega squared is negative, it's unstable, and it will stay unstable arbitrarily long time. So you will just keep growing if you're in that regime, right? It doesn't change. And so if Q is less than 1, then you can grow. And so you don't really need to care about how big the instability, the perturbations are. Perturbations on any scale will grow until they're big enough for you to care about them. So that's a feature of this theory. Q less than 1, that's for an idealized razor-thin disk. If your disk has a finite thickness, then it could be as small as, say, 0.6 for these instabilities to go. One interesting feature of the model is you do have an upper size limit from shear, and this leads to this idea of a tumor mass. You just take that wavelength of the plane waves, you make it into a circle, and then you convert that into a mass. But I would argue that this is pretty ad hoc, and it's not clear that that's going to be prescriptive in terms of helping you understand the masses you're going to get. If you go to non-axisymmetric, you get a bit of a mess. And the main reason for that is that your wavelength doesn't stay consistent with time. If everything's axisymmetric, they're rings and the wavelengths never change. However, if you're non-axisymmetric, your perturbations are sweeping through. And so the actual characteristic wavelength of those changes as they sweep through, right? So they start off very tightly wound at negative time. They sweep through and they get their largest wavelength, and then they become very tightly wound again as you go to future times. And so that means that rather than getting a nice dispersion relation, you get this ugly thing, which has tau in it, which is your time normalized to the shear time. And it looks very ugly, but then you can compare it to the dispersion relation here, and you actually have growth terms which are very similar. You have a gravity term here, you have a sound speed term, which is just trying to destroy everything, and you have shear terms related to kappa and the Oort constants. But these modifications really just reflect the fact that the wavelength is changing with time. Otherwise, you can understand it in the same way. The key takeaway, though, is that this gravity term is only going to win when you're just sweeping through, when your perturbation is radial. At any other time, when you're very sheared out, then the contribution of the sound speed term becomes very large, and so you only actually have a finite window to do anything. So unlike the Tumor model, where any perturbation can grow, you actually only have a finite time. You have to start with something big if you want to get anywhere, right? So it's different to that. So this is an example of that. This is from Jog's paper in 1992. You have nothing happens. You get close to tau equals 0 when you're swinging through radial. It's this kind of swing amplification, and then boom, you get a whole bunch of growth, but at future times that growth essentially stops. Right? So that's a feature of the non-axisymmetric structures. So we wanted to do this. We wanted to do a controlled study and look at this. So we took a disk that, the same disk as before. We didn't perturb it. It does nothing after hundreds of mega years on the right. So we wanted to put explicit perturbations in using this form. This form is essentially equivalent to a constant convergence, negative divergence at a point with a characteristic scale L, and you can also relate it to a plane wave with a similar scale. It has a peak at the same point that a sine wave would have with a wavelength L. So we put a whole bunch in a disk. This is just for convenience, so we could get 4 per run. And then we run them for a little while. So you can see there's no initial density perturbation, it's just convergence and velocity. And after a while, you potentially get structure from that. 3 of them were okay at this particular velocity perturbation. The very large wavelength one wasn't able to go. So we would call that a failure. So this is what we've been doing. We've been varying wavelengths, disk masses, the velocities of the perturbations. We like the velocity perturbations because you could argue they come from feedback or they come from compressive turbulence events or things like that. So we feel that they're a good model for what's really going on in these disks. And this is the typical behavior we get. We get success or failure. So we start with a perturbation. It starts to collapse over time. It either forms a bound nugget or it doesn't. That's kind of what happens with all these cases. What we found as an extension of the simple linear theory is we actually get some somewhat interesting mechanisms that make collapses. So we have the simple one with a nugget in the middle, but occasionally if you collapse something very, very fast, you can get a rapidly rotating ring that can undergo fission and make two objects. And also, if you have a very large scale thing that will shear apart, the shearing apart is a common behavior, and it will end up being a line mass that will fragment. But we would argue that those two are probably not that important. So here's a set of wavelengths versus velocities. Most of the time it's simple success or failure, which is the red failure, purple success. Occasionally you get the fission, but you have to slap things together really, really fast. So 25, 40 kilometers per second is pretty fast for a Milky Way scenario, so it's not going to happen very often. Similarly, for the filaments that are slow, you need a very quiet disk for that very, very long tidal feature to survive long enough to fragment as a line without something giving it a big kick. So we would argue that neither of those are very important. So this is what we get in the end. So here are all our cases. We've actually used the statistics of turbulence to try and assemble them into a typical mass, which is the gray area and the dotted line. But otherwise, these are just the whole ensemble of what we've run. So the bottom line is that for a Milky Way, for example, we get a few by 10 to the 6 as our typical mass. We get considerably less than the tumor mass, so we would argue that that is an ad hoc mass that is a significant overestimate of the kind of things you're going to get. So probably not an ideal starting point. And if you go to our warmer disks, then the usefulness of the tumor mass as a starting point actually gets worse, right? Because the tumor length in a hot massive disk can be as much as 5 kiloparsecs. It's kind of crazy that you don't expect the linear theory to work when the perturbation is on the scale of the entire disk, right? So definitely the tumor mass is not a good estimator there. And we kind of get a plateau where it's very hard for us, for any of our perturbations, to successfully make a bound structure bigger than about 10 to the 9 solar masses. So that was our conclusion from this, and this is Samantha's paper is up with all these results in them. So we also wanted to think about stars. Candle's observations are starlight, so we wanted to sort of try and transfer into that. And to do this, we took our simulation. We only took the gas above 100 solar masses per parsec squared, following suggestions by Lada that that's the star-forming gas. And then we just made that into stars at 100% efficiency. So it's a pretty aggressive way to convert things into stellar mass. And when we do that, for Milky Way-like disks, solar masses are still very low. So 10 to the 7 is kind of the ballpark we're in. And even for a very large heavy disks, candles-like disks, we're still in the ballpark of 3 by 10 to the 8 or so. And so we would argue that this is strongly supportive of the idea of what you're seeing in candles is typically multiple distinct bound star clusters that the beam is smearing together. And so just for fun, we kind of did a multiplicity thing. Like typically for the heavy disk, for example, you would have 3 per beam. And if it's a Milky Way-like analog, you might need as many as 40 per beam to build something like that. So it would be a heavily disturbed object, perhaps, where all the star formation is happening on one side to explain that. And so I encourage you to look at the paper to look at this more. I just wanted to give some preliminary advertising for the last part of Samantha's thesis that is in preparation at the moment, which is looking at the galaxies with radiative transfer. So this is an analog of a local group, not local group, a nearby object, a things type object. It's actually the Agora IC, but with much higher resolution. We increased the resolution of it. And we've been seeing what different modes of feedback do to, in terms of the outcomes, in terms of star formation and so on. So we were partly motivated by the work of Ostreicher et al. 2010. They argued that pressure balance sets star formation rates. And we have a resounding yes for this. And there's a consequence of this, which is if you really want to get your disk properties right, you need to resolve the scale height, because otherwise your midplane pressure is just wrong. So that's a strong conclusion that follows up on Samantha's earlier paper in 2016, which made this argument. But the other argument from Ostreicher et al. Was that FUV can regulate star formation in normal spirals. And for this, it's actually a resounding no, it can't. And so the FUV only case basically fragmented like crazy and had a very, very high star formation rate. So it's simply, FUV can only give you 8,000 K or so. It's really not a way to hold up a galaxy disk. So the two-phase instability goes crazy, you get lots of lumps, it just doesn't work. But what we do tend to see is that, so Wolfire suggested that FUV may be helpful in truncating star formation in disks. In the outer part of the disk, whether or not you can make a two-phase medium is very dependent on the FUV field at that point. And so we do see indications that the FUV can help truncate star formation. And the last result is we can actually match Kennicutt-Schmidt results quite well with this model too. So that's just some work in progress that you should look out for, and I'll leave my conclusions up. Thank you.
Thank you, James. Daniel?
So the initial mass of the clamps are like few percent of the mass of the disk.
Right.
So they're not really very massive. So
So
what happened after that is that so they're very comparable to what you are thinking.
So we're happy to have accretion on our clumps. We're
Yeah,
just
so they
talking
start
about the
to-
initial
Yeah, so
state. Yeah.
that's what's happening. So over the time they start to accrete, they can merge with other clamps, so they can reach as much as 10% of the mass of the disk. That would be the top.
But I would argue that there's not strong agreement on how effective that is. So we wanted to try and avoid.
Yeah, but
some groups don't seem to agree
my
with
question
you.
is, for how long did you run your simulations?
Sorry?
For how long did you run the simulations?
We're not looking at merging. So
No, but I mean in terms of orbital timescales, how many orbital periods did you run the simulations?
A few, so a couple of 100 megayears.
Yeah, maybe that's not enough to see this effect.
Reinhard?
Yeah, your talk, of course, reflects a very intense general discussion in the community over the last few years. I remember last year we had a meeting in Sexton where the theorists ranged from, tumor Q is very important to has no importance at all. And of course you showed the importance of the initial conditions. From an observational point of view, of course, you are absolutely right, and I think that Tamburello paper in that sense is correct, that we are challenged by the resolution the instruments can get at that point, but it's also clear from the beginning that what observationally we call a clump is just the upper scale. And that could still have a meaning. And indeed, now you showed the lens, the snake and other things. Let's please keep in mind that these objects have very small mass. I mean, these are not the kind of massive disks we're looking at with KMOS and SINS and so forth.
Definitely.
There is, in fact, one lens I know of, which is very massive, and so that you can analyze its power spectrum, and it has power spectrum to the high length scales. So I would say that's important. The other side, of course, of the story is it's not just size. Hannah showed you that the velocity dispersion, which is a very good thing we can measure on large scales, does what a tumor consideration would do. That's Mark's model, right? I mean, Mark's model for this increase is setting on the dependence of Q as a function of gas fraction.
Okay.
Avishai?
I think that this systematic study is very interesting and very important. However, its relevance to real cosmological valence disk instabilities is questionable. And this is because what we see, and this is work led by Nir Mandelker here, we see strong effects, external effects of interaction between galaxies, between incoming streams and clamps and so on, tidal effects that drive the instability. In particular, we see compression, compressive modes due to tides that make excessive compressive modes of turbulence in the disk that start the clamp formation. And this is a very strong effect. So, and this also gives you high Q despite the formation of clamps. So I think it's great to do it bottom up, but there's a long way to go before you have the real answer.
So, sorry, we're out of time. Okay, thanks, James. Our next talk